Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on molten salt reactors, taxonomy, and fuel cycle performance will be presented by Dr. Jiří Kripal. Doing the introduction today is Dr. Patricia Pavier. Dr. Pavier is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's the National Technical Director of the Molten Salt Reactor Program for the Department of Energy. And she's also the chair of the Gen 4 International Forum Education and Training Working Group. Patricia.
Yes, thank you very much, Berta. Good morning, everyone. Good evening. It's a pleasure to have Dr. Jiří Kripal with us today. He's a senior scientist in Advanced Nuclear System Group of Laboratory for Scientific Computing at the Paul Scherrer Institute in Switzerland. He earned his PhD in 2006 at the Czech Technical University, Prague, and the Helmholtz Zentrum Dresden-Rossendorf in Germany for his thesis entitled Dynamics of Molten Salt Reactors. At PSI, he is responsible for fuel cycle analysis and related safety parameters of Gen 4 reactors. Dr. Kripal is the coordinator of the PSI MSR research, represents Switzerland at the GIF MSR project. He has recently been nominated chair of the Gen 4 International Forum MSR Provisional System Steering Committee. He has experience in the neutronics of liquid metal and gas-cooled fast reactors and in neutronics and transients analysis of thermal and fast MSRs. So Jiří, without any delay, I give you the floor. I'm really happy. Sincerely, thank you so much, Jiří, for presenting this webinar for us today.
Okay, thank you, Patricia. Thank you very much for kind introduction, and I'm really glad to see so many people from all around the world following this seminar. And I would like to start with two disclaimers. One is that I'm typically trying to pass too many information, so I hope you will be not really too overflooded by it. And the second one is that almost exactly 2.5 years ago, I did a first seminar for this GIF webinar series about thorium and uranium cycle comparison in many reactors. And this presentation is kind of a build-up or continuation of that presentation, so you may have a look later. And it's explicitly focused on an MSR and MSR performance. So I have divided it into 7 parts. Firstly, I would like to mention the definition and taxonomy of molten salt reactors, then looking a little bit of cross-sections and reactor physics. Next would be definition or kind of discussion of 5 neutronics performance parameters. Then looking on breeding capability and core size. And subchapter from that is the breeding in open cycle, so-called breed and burn cycle. And then defining the burnup for liquid fuel, which is not so obvious. And the last part is a little bit detached. It's about radionuclide distribution and release during accidental conditions. I will also mention 3 publications during this presentation, which are more or less the source of all the information, and you can have a look later. So the definition of molten salt reactors, I adopted from the IAEA report, IAEA TRS report, which is still in preparation. I think it's not yet final version released. And the definition says that MSR is any reactor where molten salt has prominent role in the reactor core. So it can be fuel, it can be coolant, it can be moderator. And this status report from IAEA is one document which I used for preparing this presentation. And I tell you, preparing this document and preparing the taxonomy for this document was very interesting collaborative work with many international colleagues. So knowing that it can be fuel, coolant, or moderator, there is a high flexibility what you can do with MSR. So it's not a single concept; it's an entire category of reactors. Yeah, and I see now that the slides are really moving with luck. Okay, so the taxonomy was necessary, and we agreed, or we converged to something like 3 major families, and the decision was not about let's say neutron spectrum or type of salt or fuel cycle you use, but we kind of converged to something which is rather like technological. So the 3 families which we identified are yeah, and there is really a long luck when I click. The slides are not really advancing. Okay, so the 3 major classes are graphite-based molten salt reactors, where there is a graphite and salt, and it profits from the fact that graphite is compatible with the salt. Homogeneous molten salt reactors, where there is more or less nothing in the core, it's just the salt. And heterogeneous molten salt reactors, where you have some structural materials which is separating liquid fuel from another material. You can subdivide further these classes into families and types. And for instance, for the graphite-based molten salt reactor, you have fluoride salt cooled reactors. So reactors where the fuel is embedded in graphite matrix and the salt is acting only as a coolant. Then you have their graphite moderated molten salt reactors. So reactors where the fuel is diluted in the salt and graphite is acting only as a moderator. In the homogeneous MSRs, you can divide it into 2 families according to the salt type. So you have homogeneous fluoride fast MSRs and homogeneous chloride fast MSRs. The type are defined by the fuel cycle type, and for fluoride it is thorium breeder or more or less plutonium containing reactor, which covers both enriched uranium burning and transmutation, more or less. For chlorides, you have breeders, but you can have also breed and burn reactors. At that time, when we prepared this taxonomy, there was no transmuter with chloride salt, so it's not mentioned here. But of course, you can think about more types. For heterogeneous MSRs, there is non-graphite moderated MSRs, which need structural material to separate the moderator, which is not compatible with the salt. And there are heterogeneous chloride fast MSRs, profiting from the fact that with chloride salts you can get quite hard spectrum, and you can probably afford to lose some neutrons on the structural material and dedicated coolant. Of course, liquid fuel gives you enormous flexibility, so there is also a category or class of others, and these are typically obsolete or minor concepts. So I can read them. It's directly cooled MSR, it's subcritical MSRs, hybrid moderator MSR, chloride salt cooled fast reactors, frozen salt MSR, or hybrid spectrum MSR, or heterogeneous gas cooled MSRs. Those are not really followed, and those are typically obsolete. Now, for each of the 6 major families, I have an extra slide characterizing it a little bit. So for the fluoride salt cooled reactor, you can say that the type definition is based on the fuel. So if it is pebbles, or if it is a solid fuel which is not moving, like prismatic or compact, the primary heat exchange in this case takes place in the core because the fuel is solid and the salt is a dedicated coolant. And yeah, it used triso particles in the graphite matrix, and from neutronic performance perspective, it's a converter. You cannot reach breeding, and it uses for leakage utilization, it can use reflector. Typically, there are no blankets in this case. And then for illustrative, for kind of picture how it may look like, I typically take a concept which I found in the literature, which is the oldest one. Maybe it's not always the same, but yeah, typically is the case. And for characteristics, I would like to mention here that the coolant salt should be probably lithium fluoride, beryllium difluoride, because the beryllium has a certain moderation power, and this salt has therefore a negative density effect. if you would use another salt, probably you will end up, you may end up with positive effects. The specific fuel density is very low in some designs, so you may have a volumetric waste, volumetric spent fuel, and yeah, the core can be transparent for neutrons because of that. The second family are more or less graphite moderated MSRs. In this case, they are divided by the fuel cycle type. So you have thorium breeder or uranium converter. And the heat exchange, the primary heat exchange, they take place out of the core because the heat is converted by the fuel salt. And the actinides as the fuel are diluted in that salt. So typical salt used here is lithium fluoride, barium difluoride, or even lithium fluoride alone. You don't need structural materials because graphite is compatible with the salt, and you can operate such a reactor as a breeder or converter. So you can achieve breeding in thorium cycle, of course, only. And for leakage utilization, you can consider not only reflector, but also multi-zone core, like in the case of MSBR, or even blankets. For characterization, the specific fuel density typically is higher than in fluoride salt cooled reactors, and the graphite lifespan is limited by its irradiation because there is no fuel inside, so it's not limited by burnup, it's just the lifespan due to irradiation of graphite. Hastelloy vessel is protected by the graphite, so it has a longer lifespan, and if you want to breed, you may need to swiftly remove fission products and even protactinium. Yes, so let's go to the third family. It's homogeneous fluoride fast MSRs. The types here are defined again by the fuel cycle type, so it can be thorium breeder or converter or burner. Since the actinides are diluted in the salt, again the primary heat exchange takes place out of the core. There are no structural materials, it's homogeneous, just the core is just filled by the salt. It can act as a breeder. It's slightly more relaxed, the neutron economy, so you don't need so fast fission product separation like in the MSBR, as in the thermal breeder, but still you need to do it. And in this case, there is no graphite protecting the vessel, so you may need to regularly replace the reactor vessel. And you don't use beryllium in this case because beryllium is a moderator, but the lithium fluoride which you use is also has certain moderation power. So it is fast reactor, but it has the fastest, softest fast spectra you can imagine. At the same time, it has low transparency for neutrons, so you can end up with possibly quite compact cores. The next, the second homogeneous are the fluoride fast MSRs. Again, types are defined by fuel cycle. So it can be a breeder and uranium plutonium cycle or even breed and burn. I don't mention here thorium cycle, I will come to it later. Again, actinides are diluted in fluoride salt, so the heat exchange takes place out of the core. And for leakage utilization, you use blanket or a reflector. The first design I found in the literature is from 1956 in this case. Again, you have the same issue as in homogeneous fluoride fast MSRs. The vessel is irradiated by neutrons, so you may need to replace it very frequently. And compared to lithium fluoride, which I mentioned earlier, in this case, you have typically sodium chloride, and there is kind of absence of scattering or moderation power in the salt. So these reactors can be quite transparent for neutrons. As a consequence, you have very hard spectrum, but also you may have a very large reactors. The fifth family are non-graphite moderated molten salt reactors. Here it is a little bit more complicated to discuss it because the types definition is by the moderator state, so you can have solid or liquid moderator. For the liquid moderator, let's name a heavy water or sodium hydroxide from the two startups from Denmark. And it's not easy to conclude if the primary heat exchange takes place in the core or not, because in some cases you can decide that the moderator will act as a heat exchange medium, and in some cases you can say, no, I will still use salt as a medium which is converting the heat out of the core. Breeding in these reactors is questionable because you really rely on the neutron economy of the structural material which is separating the fuel from the moderator. And the example here is from 1954, from the kind of scoping period where people looked on many different designs. And of course, in this case, the limited lifespan is of the separation material, so of the tubes which are in the reactor. And the tubes or the material also determines the neutronic performance. The last family are heterogeneous chloride fast MSRs. So in this case, you put the salt into a fuel pins and it's surrounded by dedicated coolant. So salt typically does not have heat exchange function, even though you can decide other way. But since you put the fuel in pins, you don't want to pump the salt extensively. Again, typically you rely on sodium chloride or other chlorides. You can breed. You can use it as a converter. A breed and burn, it's questionable, theoretically possible, but questionable. And in this case, probably this is not the oldest design, but I pick up this because it's a Swiss design from 1972, where the fuel salt was cooled by blanket salt, actually. Again, lifespan of separation material, reducing the neutronic performance, but possibly may provide some scattering. So maybe it may result in smaller cores. Nonetheless, I cannot say from my own experience, because for the heterogeneous MSRs, I have the least experience from these 6 families. And it is because the design data for these reactors are typically not available. It is much easier with graphite moderated reactors or homogeneous reactors than with these heterogeneous reactors. So now let's have a look what materials can be used in these reactors, yes, in these 6 major families. So there are, I identify here 4 groups of materials, like water-like, so hydrogen, deuterium, oxygen, or liquid metals, or gases, or salts, including like 2 isotopes of lithium, beryllium, fluorine, natural magnesium, chlorine 3537, natural potassium, calcium. Okay, sodium was already included in the liquid metals. And I had a look on a cross-section, so typically on a capture cross-section, as you can see here. And in this plot, the color scheme is selected so that the brown curve, typically you see it's lithium 6, indicates a high capture, and the edge kind of middle capture rate is lithium 7. So whatever is above lithium 7 is brownish, and once you are below lithium 7, you get to green scheme, and dark green is really low capture. So the capture cross section was determining the color scheme. And if you look on scattering cross section, you see that there is no correlation between capture and scattering. The colors are really randomly distributed here. And you can also see that they have a different shape. So the capture cross-section is strongly evolving with the energy of neutrons, whereas scattering cross-section have certain plateau there. It's very hard to discuss and analyze these charts. So what I did, I have averaged the cross-sections in 2 energy ranges, in energy range of 0.1 electron volt and in an energy range of 0.1 mega electron volt. And if you do this averaging, what you obtain, for instance, for the thermal scattering is this chart. And here I would like to say that the order of the nuclides is selected so that the most scattering is on the top. So it's hydrogen, but the color, which is representing capture, is still preserved. And to discuss a little bit more how these materials can moderate, of course, you need also to include the logarithmic decrement of energy, C, and I did the product of these 2 to define or to generate something like moderation power. So you can say microscopic moderation power, which is not really a classical definition. And if you look on this moderation power, you see that hydrogen is the best. Yes, it's really by one order better than everything else. Deuterium is the second, with more or less 10 times lower moderating power, and beryllium more or less 20 times lower moderating power. Surprisingly, number 4 is chlorine 35, but we don't use it as a moderator. And the reason is simple, because it has a tremendous capture cross-section. The second, or the first, from this perspective, is lithium-6. So we are typically enriching lithium to get rid of lithium-6 whenever lithium is used in thermal spectrum, even in fast, I would say. And typically, the chlorine is also enriched if you want to improve your neutron economy. Now you can have a look on moderation power in fast neutron range. Okay. Yes. And it's fairly similar chart as in the thermal range, but I would like to point out here that, for instance, fluorine, it has a higher, it's a more strong moderator in the fast energy range. It's not really moderator, but it's a kind of, the moderation power in fast energy range is higher. The same is valid for lithium and, for instance, magnesium. And the reason is that there are resonances of scattering cross sections which are increasing actually the average cross section. So this is the reason why, for instance, lithium fluoride, it's not a moderator, but it's suppressing the spectrum. And then you can have a look on fast capture, where, okay, lithium-6 is outstanding, it's really capturing a lot. Other materials are, let's say, okayish. Of course, again, chlorine 35 is questionable, but it's comparable to lead. So you can use these data and you can kind of conclude which nuclides are moderator. So of course, you know all of them moderator, and which nuclides are suppressing fast neutron spectrum. So here I would like to point out fluorine or lithium-7 or magnesium, which nuclides can be used for breeding in thermal spectrum. So typically all moderators, but not hydrogen, because of its higher capture, and which can be used for breeding in fast spectrum. Here you exclude moderators, and yeah, in case of fluorine you can do that, but the soft you get really soft fast spectra. I have another slide about other materials. I will not spend much time here, just mentioning that nickel, which is often used in alloys, has roughly twice higher capture cross section than iron, and that silicon, which is sometimes together with silicon carbide, foreseen for kind of good economy neutron cores, is quite good from capture perspective and scattering perspective. Okay, so I wanted to characterize in this presentation actually these reactors from for reactor physics, from reactor physics perspective. But once again, we have 6 families. We have fluoride salt-cooled reactors. We have graphite moderated MSR, homogeneous fluoride fast MSR, homogeneous chloride fast MSRs, then non-graphite moderated MSRs, and heterogeneous chloride fast MSR. So it's not straightforward to do that, and I will do it very briefly, just making a bullet-wise list of features or issues. So I would like to mention double heterogeneity, which is relevant for the first family. It's more or less, this first family is kind of cross-breed of HDR and MSR. So it has the same issue as HDR. Next one is the graphite limited lifespan and possible positive temperature effect. Of course, for graphite moderated MSRs. You can have positive coolant and blanket density effects in the systems where there is a dedicated coolant. You can have large migration area. So typically in graphite moderated reactors or in reactors with chloride salts. Fuel volumetric heat up and homogenization. This is valid for all reactors where there is liquid fuel. Power level determination and the peaking in the core is the opposite, is in the reactors where you have either solid fuel or liquid fuel in pins, where the heat exchange surface is determined by the pin geometry, and you have issue of the power peaking. Yes. Local overheating and excessive burnup. It's valid for reactors with liquid fuel, where you can have stagnation zones or a little bit of fuel salt enclosed by structural material. Fission product circulation, or you can say this famous delay neutron drift. So again, for all reactors where the fuel is extensively circulated or pumped through the reactor. Removal of gaseous and non-soluble fission products. Typically, it is applied because it helps to improve the neutron economy, but it also has some impact on the core layout and so on. And Protactinium-233 longer half-life. It has roughly 11 times longer half-life than Neptunium-239. And in some cases, you really need to separate the protactinium from the reactor so that you can let it to decay outside of the neutron flux to reduce its parasitic capture. And limited structural material lifespan. So more or less in all families, you face it more or less. So, and here I would like to mention that after this IAEA report about molten salt status, the second report I really rely on is the Molten Salt Reactors and Thorium Energy. It's a second edition of a book which is in preparation. And I'm not sure even if I could present what I do just now, because I am more or less presenting some outcomes of this book. It should be the chapter 4 about reactor physics, but I use it as a kind of chance to advertise this book. Okay, so there are 5 neutron performance parameters, where the first foremost is breeding capability. And if you think about it, it's straightforward. It's more or less indicating how many neutrons can be captured on uranium-238 or thorium-232. It's nothing else than that. How many neutrons you can waste or lose being captured on these two materials. And the reason why we are typically enriching uranium is the exact opposite. You want to reduce the capture of uranium-8. So you want to reduce breeding if you are enriching your fuel. Okay, it also depends on the reactor type, so it's not fully so straightforward. So it's about neutron economy. And I would like to name for MSR here that you can avoid structural materials in many families, so it can help your neutron economy. The second parameter is achievable burnup. And it's limited by fission product parasitic neutron capture and, of course, fuel irradiation stability. It depends on initial reserve of fissile material, so it may be much better in the breeders. And here I would like to name the radiation stability of the salt. So it's not limiting you, you are limited by the other factors. Now, initial fissile mass as the third parameter, of course, again determined by neutron economy and spectrum time. And sometimes if it is not a breeder, you need to a higher initial excess of fissile material to reach higher burnups. And here I would like to name online refueling and removal of some fission products, which is also relevant for the achievable burnup, of course. Fourth parameter is a means of criticality maintenance. So the change of actinides and buildup of fission products results of reactivity oscillations, and the compensation needs may differ between reactors. And yeah, okay, you have liquid fuel, so you have chance to reshape or drain the fuel from the reactor in ultimate case. And the last one is transmutation capability. So roughly speaking, it's neutron costs and speed of synthetic actinized fission. So of course here you also need compatibility of the fuel with synthetic actinides. So this may be the big advantage of MSRs if they would be used as transmuters, that there is absence of fabrication step, and solubility of the respective actinides is kind of limiting factor here. So from these 5, of course, the breeding capability is the most important, and all 5 depends on neutron economy. So neutron economy is also determining 4 reactor classes based on the breeding capability. Burner, as the first one, more or less avoids fertile materials like uranium-8 or thorium-2. So it has the lowest neutron economy from this perspective, and it's meant for burning of synthetic actinides. Converter, typically like light water reactor or denaturated MSR, use enriched uranium, and the discharge fuel finally contain some plutonium, more or less the same amount of plutonium as of uranium-5. In breeders, let's speak here about the uranium-plutonium cycle as on the illustration. You preserve the fissile mass, so you discharge fuel which has the same fissile mass as the initial fuel, and you profit from this only in case you really recycle the fuel. And then in case you have really excellent breeder, which is overbreeding, you can even operate it in breed and burn mode, where you load fuel from depleted or natural uranium, and you discharge fuel with a lot of plutonium. And in average, the core is critical. Now, for the purposes of the next few slides, I need to do a small detour to nuclear physics, because irradiating of thorium-2 and uranium-8 results in kind of irradiation chains. And I would like to show you nuclide charts, and I would like to point out that there is kind of a repetitiveness of actinized properties with a period of 2 protons and 4 neutrons. So if you look on the nuclide chart, you can see that thorium-2 and uranium-8 are at the same position from the stability line, and this is probably the reason why we have them as a primordial actinides on the Earth. And for plutonium-244, which would be the next one, it was nearly possible to be primordial nuclide, but unfortunately the half-life and the age of Earth didn't allow it. And now the irradiation trajectories or chains are very similar for these 2 nuclides. But there is one big difference. In thorium chain, at the position of uranium-5, you have uranium-5 at certain position, which has a very long half-life and decaying by alpha decay. At the same position in plutonium or uranium-8 chain, you have plutonium-241, which is decaying very, very fast with beta-minus decay. So this is the major difference between these chains. And second thing or third thing I would like to point here is, in general, there are more nucleons in uranium chain. So in general, all the elements have slightly shorter half-lives, but for the same reasons, typically they also produce more neutrons per fission. Now, I spoke about neutron balance, and I don't have time to go in real detail, but neutron balance has components. One is neutron leakage. Second is, let's say, parasitic neutron absorption on non-fuel materials. And then you have the neutron balance of the actinides itself. And I really like the very famous eta -2 neutron balance as an indicator of breeding. But if you look in detail on it, you need to introduce correction factors to see the reality. So you should account for fast fission of on the fertile material. You should account for parasitic neutron captures on the daughter product. So in case of thorium-uranium cycle, you should consider parasitic neutron captures on uranium-4 and its daughter products. And the last term also includes the parasitic neutron capture on protactinium, which leads to uranium-4 and its daughter products. So this is the neutron balance you can do. And the reason why you can do it so nicely is that, or why I could do it so nicely, is that I was doing it for equilibrium state. So I had equalized composition of uranium-8 and thorium-2 irradiation chains. And you can do this balance many different ways. This was first one. The second one is you can just do nu minus 2. So you take all the neutrons you have from fission, you subtract 2 neutrons because you need one for fission, one for breeding. Then you have fast fission on the fertile, and then you have capture of actinides as a kind of a correction factor, and end-to-end reaction as extra neutrons. You can do also like a neutrons per fission, and you can subtract the neutron cost of fission. So for instance, if you fission uranium-3 and you know it's coming from thorium-2, it costs you 2 neutrons. If you would fission uranium-5, it will cost you 4 neutrons. And the last is the simplest, more or less the neutron balance of thorium irradiation chain is nothing else than the famous D factor of thorium-2. I will not discuss what is D factor. You can have a look in the literature, but more or less it's the neutron cost to burn certain nuclide together with its daughters. So I did enumerate these neutron balances for the first 4 families, because I don't have much data for the 5th and 6th for the heterogeneous MSRs. Yeah, there is also migration length in the table. You can see the first line, and you can see really that chloride salts are really transparent for neutrons, and the same is valid for FHR in case of pebbles. And then I will not waste time here going to details, but I will show the first balance, so the eta minus 2. If you would just do eta minus 2 without any correction, you would get something which is ranging from 0.18 to 0.31, so neutrons per fission. And it looks very nice for thermal spectrum, but then you need to introduce the corrections. And for instance, in the case of FHR, you see that from 0.21.25 you drop down to 0.06 neutrons. Yes, because of parasitic absorptions of higher nuclide. So very often some people present a paper about breeding and they say, yeah, it can breed, but the statement is valid for a fresh core or is valid for the first fuel cycle. It's much different if you go for the second, third, fourth cycle and you build up the higher actinides. The second balance, of course, you end up with the same numbers, but you start from eta minus 2, which is less accurate than eta nu minus 2. So it is less accurate than eta minus 2. And firstly, with the correction factor, especially with the capture of actinides, you get the right numbers. And then the fission costs, again, the same results, and the D factors, roughly the same results. Now, with one click, I will change these numbers from thorium cycle to uranium cycle. And what you can see immediately here is that there is much steeper slope. The neutrons are more or less, the balance of neutrons is negative in all thermal reactors, and it's much stronger positive in fast spectrum. And the edge, when it is becoming positive, is between MSFR with Fly-B and Fly salt. So whenever you have beryllium in the salt, you cannot breed in uranium-plutonium cycle. When you remove beryllium, you can theoretically. Okay, yeah, you can make it graphical to make it easy digestible. So obviously, uranium-plutonium cycle is quite good or excellent when you have hard spectrum. Thorium cycle is more balanced, and therefore you can potentially breed in thermal spectrum. Yes, so graphite moderated reactor only can breed in thorium cycle. For fluoride fast MSR, you have kind of equal performance and almost epithermal spectrum. For chloride fast MSRs, you can go for both reactors, but you can already now see that the neutron balance, the excess of neutrons in thorium cycle is almost half of that one of uranium cycle. And this will have big consequence of the core size. And the breed and burn mode is only possible in uranium-plutonium cycle. Okay, the other parameters, I will just go swiftly through it because I don't have anything equally elaborated. So for achievable burnup, I would like to point out that it's mainly a question of ratio between fission products and fissile actinides. So if you have a reactor which is breeder in thermal spectrum, you have a lower reserve of fissile actinides. You are much more sensitive to fission products. So in fast spectrum, on the other hand, if you have more than 10% of fissile actinides, you can of course afford 10% of fission products much easier than in thermal spectrum, where you have 1 or 2% of fissile material and 10% of fission products would represent 5 to 10 times more of something absorbing than something fissile. Yes. The initial fissile mass, again, here is only the specific density of fissile nuclides in these MSR examples. Of course, in the thermal spectrum, typically you have less actinides, and from these actinides, lower percentage is fissile. So you can really have much lower initial fissile mass in these reactors. For means of criticality maintenance, I don't even have an illustration, so it's quite boring slide. But okay, you have a liquid fuel. You can remove fission products. You can add actinides. You can use unusual reactivity control methods because the salt is liquid. You can expel the salt by kind of empty cylinders to tune the reactivity. And for accidental conditions, you can even think about kind of overflow systems and so on. For transportation capability as the last parameter, typically you should have a look on the radiotoxicity balance if you are in open cycle or on reprocessing losses. But you can also have a look on speed or pace of transportation, which is proportional to the cross-section. And of course, the cross-section is always higher in thermal spectrum. And you can also have a look on neutron costs. So how many neutron it costs. So I have an example here for plutonium-242. And you see that in thermal spectrum, it consumes 1 neutron to get rid of 1 atom of plutonium-242. And in fast spectrum, it almost produces 1 neutron for the same, because of the fissile daughters, which are in the chain of plutonium-242. Okay. Now I will again look on the breeding capability, but in a little bit more realistic cases. So in my previous presentation 2.5 years ago, I was already showing this slide where we looked on 5 different fluoride salts and 6 different moderators. And the outcome was a kind of parametric study where we changed the salt share. So on x-axis, there is salt share in the core. And on y-axis, there is a channel radius, so kind of heterogeneity study. And what you can see here is that lithium fluoride is neutronically the best salt, that heavy water and beryllium are really good moderators. Yeah. You can more or less forget hydrogen if you would like to breed. And graphite is nothing special. Just it is the only one which is compatible with the salt. So you can directly use these results, which didn't include the separation, the structural materials for separation of the moderator. If you would include it, for instance, in the beryllium or heavy water case, you would get a curve like this, where the full line is the original performance and the dashed lines are for 3 different separating materials. And obviously, only thing which works is silicon carbide or carbide composites. So I'm joking on this slide usually that purely from neutronic perspective, we can design heavy water boiling MSR. Okay, let's have a look for fast reactors. So for homogeneous fast MSRs, similar study, 5 fluoride salts, 3 chloride salts, and analysis of the performance. This is very convoluted chart. It is based on one of the reactivity balance method. But what we can see here is that from chloride salts, the enriched sodium chloride is the best. And from fluorides, again, is lithium fluoride. The beryllium, because it's moderating, really does not help in the fast reactors. And actinides, chlorides, the last column I kind of neglect because the melting temperature of that would be probably too high. The same for uranium cycle, looks similar, but the reactivity excess for sodium chloride, enriched sodium chloride salt, is much higher. So this is also the reason why you can think about breathe and burn. You can also operate it with natural chlorine, and there are 4 almost equal salts for fluorides. But of course, the question is if you can at all operate it because of the limited plutonium trifluoride solubility. Now let's have a look of the core size. So if you would compare it directly with the classical lead, sodium, and gas-cooled reactors, which are shown here, the homogeneous fluoride salt-based fast reactor would be roughly big like this, the blue square. In uranium plutonium cycle, it will be slightly bigger. And if you will stay by uranium plutonium cycle and switch from fluoride to chloride, you will get more or less the same performance. The difference between 5 and 6 in size is small, but it is by chance, because in chlorides, the core is really transparent and profits from really high K infinity of the salt, whereas in fluorides, the core is kind of scattering neutrons and the K infinity is much lower. So by chance, they are almost equal. If you would change to thorium cycle in fluorides, you have lower K infinity and the transparency makes the core really big. And for comparison, this is the size of MSBR designed in Oak Ridge. But okay, here the salt content in the core was only 13%, so it's not the same as a homogeneous reactor fully filled by salt. Okay, so you can also do kind of criticality line using the Fermi-Baire core theory, because you know the migration lengths. And on these lines, you can see the position of uranium plutonium cycle and thorium uranium cycle. So if I just skip to another side, it shows you that whenever you have a fast spectrum, uranium plutonium cycle is performing much better, provides you much smaller reactor. And the edge where it is changing is somewhere around MSFR with lithium fluoride salt, where these 2 points are more or less on the same spot. And if you put beryllium in the salt, if you have Fly-B there, you cannot at all breathe with uranium plutonium cycle, only with thorium cycle. The core size also depends on the breeding gain you wish. So I was showing the core size for breeding gain 0, so for iso-breeding reactors. If you would like to have lower breeding or higher breeding, of course, you must change the core dimension respectively. And thorium cycle is much more sensitive for that, so you may need to exchange the core size more than in uranium plutonium cycle, of course. Okay, I have still 3 topics to speak about, so I need to a little bit speed up. So there is also self-sustaining breeding option in an open cycle, which is called breathe and burn. In solid fuel case, you load assembly, which is from depleted uranium. It is traveling or reshuffled through the reactor, and you discharge the most burned assemblies. And the core is critical because in average, there is enough plutonium. In liquid fuel case, you load the same depleted uranium with a salt, and what you have in the core is, in case of single fluid, it's average composition. So you are discharging average composition, not the most burned composition. Of course, this may change if you have a multi-fluid, but you still discharge the average composition in the last volume. And there is something like fuel residence time distribution. And the burnup, average burnup of the salt, more or less is a function of this residence time. And of course, also of the fission product share is also a function of the reprocessing or removal of fission products. So for that breeding, you can define a simple criteria, because the fuel or the salt you are discharging includes fissile material, and your conversion ratio and your burnup must be so that the fissile material you are discharging is an excess. You will not miss it. So you are discharging fuel which includes excess of fissile material. And to achieve that, as an example, if your conversion ratio will be 1.2, you need to reach burnup which is 5 times higher than the fissile share. So if you have fast reactor with 10% fissile actinides, you need to reach 50% burnup with conversion ratio 1.2, so that the fissile material you are discharging is just the breath excess. So this makes the breathe and burn a little bit challenging, and it's always question of the core size, because you would really like to minimize leakage. Here I have curves for equilibrium K infinity. So if you simulate this breathe and burn on infinite lattice, you can see that in thorium cycle it's nearly impossible. In mixed cycle maybe, and for uranium cycle it is possible, and the more actinides you manage to pack in your salt, the better is the performance. So of course the smaller is then finally your core. But it's question if chemistry and melting temperatures will allow for something like very packed actinides in the salt. You can then compare the core size for closed fuel cycle and breathe and burn open cycle. And because you need to utilize the leakage more in the breathe and burn cycle, of course, you end up with bigger cores. Okay, now I wanted to also speak a little bit about the burnup definition. And let's start with solid fuel reactor, where it is, I hope, straightforward. So if you have a burnup which is defined like gigawatt days per ton of heavy metal, you integrate the power you produce and you divide it by the mass of actinides you load it to the reactor to produce that power. You can also define it as a FIMA percent. So you integrate the fission rate and you divide it by number of actinides atoms you load it to the reactor. So both definitions, I hope, are quite straightforward. And the fission product share in the core is more or less equal to burnup if you express it in the FIMA percent units. So it's straightforward and relatively easy to understand. In liquid fuel, it's a little bit more complicated, and you can define the burnup as a differential property. So you can divide the current power of the reactor with a mass of actinides you are refilling to the reactor in case of stabilized operation. If you do this in FIMA percent, is fission rate divided by atomic concentration or total number of atoms you are refilling to the reactor. And you can approximate this a little bit by the balance of actinides or balance of fission products, but it's much more complicated. And you can also have integral definitions, more or less, where you do integrate these properties, but in that case, you need to account also for the initial actinide mass you loaded in the core. So obviously, these two definitions will differ between each other, and they also differ from the definition from solid fuel. I have now two examples what it can cause. So first of all, that the share of fission product is not equal to the burnup in FIMA percent. So I showed a curves showing the K infinity evolution as a burnup for the breathe and burn reactor. You can see it again here in this chart as a function of differential burnup. But you can plot it also as a function of fission products share in the core. And one of the first publications we did about breathe and burn was including this information. So it was the curve as a function of fission products share in the core. And if you replot the same curve for the differential burnup, if you account for the fact that fission products are removed from the core, you get slightly different profiles. Another point I have here is that if you have stabilized operation for a long time, the integral and differential definition will converge to each other. And here I have the more or less integral definition of burnup for a breathe and burn reactor. And you see that it starts at 0 because the initial mass of actinides in the core is tremendous. So it takes a long time that you see some reasonable integral burnup. But the longer you operate the reactor, the more it converges to the differential burnup. Okay, this was kind of theoretical intermezzo. I am coming to the last part of my presentation, which is a little bit detached from the rest. and it's about radionuclides distribution and release during accidental conditions. So as I mentioned, molten salt reactors may profit from the fact that you are removing fission products from the reactor. And I pick up as an example here the Evol and Mars benchmark, which was based on this MSFR core developed in Europe on simplified geometry of this core. This core is based on lithium fluoride carrier salt, typically in thorium cycle, and has a blanket. And there are two major reprocessing streams. So there is a removal of gaseous and volatile fission products with cycle time of 30 seconds. And then reprocessing of the fuel salt with a cycle time of 450 days. I would like to stress here that zirconium with proton number 40 is not included in the gaseous and volatile fission products. So it's not really removed by bubbling. And if you simulate this reactor, then you can get a distribution of radiotoxicity, let's say, normalized per 1 cubic meter of the salt. And after 200 years of operation of such a reactor, and it's immediate radiotoxicity after shutdown, yes. So it may change within minutes or hours, but immediately after shutdown, the major component of radiotoxicity is in the off-gas system. So from this 15 presented decay chains of fission products or actinides, more or less in 13 cases, the major component is in the off-gas system. Only in 2 cases it is in the core. First case is the rank 11, where it is caused by protactinium and thorium 3 decay, and rank 14, where I even don't know, it's probably fission products which are not removed by off-gas system. Okay, so there is not much left in the fuel salt, but once again, this is immediately after shutdown. So what we did in that study is that you anyway assume that you have a fuel salt which can be spilled. So a simplified containment was considered, and an idea that there is some leak of salt and all the fuel salt was spilled to the bottom of the containment, and that it was heated up by decay heat in 2 hours to 1500 kelvins. And now we try to simulate what will be released from that spill. And for that we used Melcore, loosely coupled with GEMS. GEMS is thermodynamics code providing the properties of compounds to Melcore, and it relies on a Heracles database for that case. So we needed to update a little bit. The Heracles database includes some new species, and to have something which can calculate the activity coefficients and provide it to Melcore. So I have 3 slides of examples of the results. So the mass release as a function of fluorine content. So the middle chart is for stoichiometric case. The left one is when you have 1% less fluorine, and the right one for 1% more of fluorine. And these 3 charts are only for actinides, actinide species. And you can see that there is quite strong dependency, typically for uranium pentafluoride and thorium trifluoride. So thorium trifluoride, when there is less fluorine, is dominating. When there is more fluorine, it's almost not there. And the opposite is for uranium pentafluoride. When there is less fluorine, it's almost not there, and when there is more fluorine, it's dominating. The same was obtained for fission products, but the dependency there on the, let's say, redox potential of fluorine content was not so strong. And you can process the results, and you can also look on released activity in becquerels in form of aerosols on the left and vapors on the right. And ultimately, you can then conclude what is your major carrier of radiotoxicity. And what we find out in that case, the major carrier is zirconium. And now, of course, the question is, okay, zirconium trifluoride, it's a tetrafluoride, it has higher vapor pressure. So why it is at all in the salt still? Why it doesn't leave the salt through the off-gas system? So this is kind of open question, and it could be that if you change the simulation of the off-gas system, that this radiotoxicity component will be not evaporating from the fuel salt, but it will be present rather in the off-gas system. Okay, this was a part which does not really fit the overall frame of the presentation because it was not so much related to the fuel cycle. But the removal and the reprocessing of the salt, of course, it's strongly influencing the fuel cycle performance. And often if you want to create your own design, what you do, you include some coefficients of removal, and often these parameters may be not realistic. This was probably the message related to the fuel cycle. Okay, that's all I prepared for today. So I hope that it was understandable and not really too fast, and I hope you will have some questions.
Thank you, Yuri. Before we move to questions, we'll take a quick look at the upcoming webinar presentations in February: Safe Final Disposal of Spent Nuclear Fuel in Finland. In March, Advanced Reactor Safeguards, Materials Accountancy Challenges. And in April, a presentation on an overview of nuclear graphite R&D in support of advanced reactors. There have been questions regarding the handouts, and I apologize for the formatting. It's been pointed out that the sizing was incorrect, and there's some garbled characters. That's been corrected, but unfortunately, I cannot post them during this webinar presentation. So be advised that they will be uploaded. The proper ones will be uploaded to the GIF webinar, the GIF website at www.gif-4.org following the presentation. It is recorded, and that webinar recording will also be made available. Yuri, I've elevated you so that you can read the questions also. The first one is the N2N reaction with designs containing beryllium should affect neutron economy there?
No, if you speak about the neutrons based on beryllium, no. It's it's not in the balance. In the actual simulation, it may be there, but not in the balance, not post-process in the balance.
Thank you. Have you also quantified neutron balance and other characteristics for MSRs, and the hypothesis of using thorium plutonium as startup fuel could be generic plutonium vector similar to that of fresh MOX fuel?
We did some analysis how to start thorium fuel cycle and to use, for instance, reactor grade plutonium, but I didn't show it much in this presentation. You may have a look on the previous presentation 2.5 years ago. But in this presentation, it was mainly focusing on the equilibrium vector, because the beauty of the equilibrium vector is that it's only one. So if you give me a reactor design, I can calculate this equilibrium vector and its eigenvalue of the system. So knowing this eigenvalue, I can assess the performance of the reactor. And it's only one kind of set of data. Transition from different plutonium vectors, it's published. We did it, Boris Homburger did it. I'm co-authoring the paper, so you can try to find it. You have many options how to do it. If you will keep the material in the reactor, or if you put it in the blankets and you will accumulate the material somewhere outside. So there are many other options. So I didn't include it in this presentation yet. But of course, if you have plutonium, you profit from almost 3 neutrons per fission. It's much easier, so to say, to breed new fuel with thorium material. Yeah.
Thank you. What condition needs to be achieved for complete burnup of transuranic elements in the fast reactors?
Yeah, okay. This is equally good question as how to define the transmutation performance. So in fast spectrum, you have the advantage that if you start to burn, for instance, the plutonium-242, ultimately you will gain neutrons from its transmutation. But it does not tell you how many daughters you will generate and how long it will take to burn it. But roughly speaking, I mean, if you think about efficiency of burning, you can say I have reactor with installed power. This reactor will burn in 1 year X tons of actinides. So the question is only how many percent from this mass will be the material I want to burn, and how many percent will be the material which was bred and I didn't want actually it to be burned. So yeah, there is no generic answer, but for any system you can say, okay, how many percent of the material I loaded was burned from the mass which was burnt in total.
Thank you. That's all the questions I see that have come in. Again, there's several dealing with whether or not the webinar was recorded and available. And again, it is. It has been recorded. It is recording now. The recording and the slide deck will be posted to the GIF website. Just give us a couple days to get that rendered and uploaded.
Yeah, I don't know. I see also a raised hand, but I don't know if this is still actual. Maybe it was 78 minutes ago, so probably not actual anymore. Yeah.
Yeah, that I don't see one now.
Uh-huh. Yeah, so if there should be not another question, I will just repeat that there are 3 sources of literature you can have a look. One is the IAEA report. The second one is the Dolan's second edition of the Thomas Dolan's book. And the third one, which probably I didn't stress enough, is a set of 3 chapters in Elsevier Encyclopedia dedicated to self-sustaining breeding. Yeah, so if you Google or if you have a look on the references I mentioned in my slides, and there are three parts of self-sustaining breeding documents where many things which I presented are described.
Great, thank you for sharing that. Thank you again for sharing your expertise and presenting all of this information. It's very interesting, and you can tell from the number of participants and the interactive questions and answers the level of interest. Patricia, do you have any closing thoughts?
No, I think it was a very good webinar. I would like to thank Yuri again for the presentation. And like Berta said, we have a YouTube channel, GIF Education and Training Working Group. So you will have the presentation available on the YouTube channel as well as the GIF portal. So I would like to thank all the participants, and we'll see you in a month.
Thank you.
Thank you.
With that, we'll close. Bye-bye.
Yeah. Bye-bye, everyone. Bye.